Greetings and welcome to the Chemistry 150 lecture for Chapter 3, Sections 3.3 through 3.5, where we're going to look at how the electrons are based around atoms in a lot more detail. And this is a pretty interesting chapter. We talked a little bit about protons, neutrons, and why electrons are important, but we're going to see in this section some really strange things that are quite different from our day-to-day reality. We talked earlier about how protons and neutrons are in the nucleus, and electrons kind of circle around the outside, but we didn't really go into their nature as to what they're doing on the outside, and that's really important for this chapter and for chemistry in general. Most chemical reactions involve transferring of electrons from one species to another. So from reactant to product or reactants to product or whatever. But electron transfer is a big thing. Some chemical reactions are more about the nucleus, but that's a whole different ballgame. And we'll talk about those in the Chem 200 series a little bit. But most regular chemical reactions are about electrons. And so we need to know kind of where they are, how much energy they have, how easy it is to transfer them and stuff like that. And that's what this section is going to get into. But the answers as to what electrons are up to was a lot different than most people thought it would be. And the type of the study that people use to explain the nature of electrons and atoms is called quantum physics. Sometimes it's called quantum mechanics, sometimes quantum chemistry. They're all the same thing. And this is a very, very strange field. You're going to look at some things when you go into quantum chemistry and quantum physics that'll make you go like, whoa. It's kind of hard to explain right now, but trust me, it is. The little picture in the lower right corner is about a guy named Max Planck, and he was one of the big people that moved quantum physics along pretty well. And you can see before and after this, after learning about it. And anyway, it's very cool. I think it'll give you a lot of things to think about, and it's a pretty fun chapter. We're going to hit this section a lot harder in the Chem 200 level, but for right now, we'll give you an overview, kind of see some of the things we'll talk about. People didn't always understand where electrons were, and one of the early models of the electron was what they call the plum pudding model. A guy named J.J. Thomson, who was pretty cool, came up with this idea, and there was some evidence for it. And in the plum pudding model, the atoms were kind of like spheres. There was a positive charge from the protons over the whole sphere, and inside the sphere there were these little tiny negative points of electrons. The plum pudding model is totally fine in chemistry and science in general. You always propose something and then move on. In the plum pudding model, you had large volume and negative spheres in an overall positive cloud, and the density was relatively low. But then we saw earlier how Rutherford's gold foil experiment kind of blew this out of the water. In Rutherford's gold foil experiment, which is the current and hopefully correct model, there was a very, very, very dense nucleus in the center of the atom, which was positive. And the electrons, which kind of went around the outside, were very low density, not a lot of mass per unit volume. So most of the atom was actually empty. Only in the center of the atom in the nucleus did you have really an appreciable mass. That worked okay for a while and stuff, but then there was still questions about how electrons exactly were around the nucleus. And the first person that came up with some really cool ideas, his name was Niels Bohr. And the Bohr model of the atom can still be used, and we'll talk about this more. But anyway, in the Bohr model of the atom, he thought about them as being like different spheres, and electrons would want to be in the lowest energy possible, lowest energy being negative electrons closest to the positive nucleus. So they'd want to be in level 1 first, and then level 2 would be the next best one, if you will, level 3 after that, etc., etc. Ground state is the term used for being in the lowest energy possible. And for hydrogen, the ground state, the lowest energy, is if that electron is in the first sphere or orbit. Now, later on, the name orbit was changed to shells. We're going to talk about how there are shells around electrons, and they start with 1 and go up in progressively higher numbers in whole number increments. Bohr was the one that thought about this shell, and that's pretty cool. Bohr's great for hydrogen. His shell idea actually worked really well, but it didn't work so well for other atoms. And it's interesting that even today, all right, the Bohr model for the atom works really great if you have only one electron in your atom. So for example, Bohr works really great for hydrogen, and it works really great for helium plus 1, which has only one electron. But once you get into more electrons, Bohr kind of falls apart. So Bohr was great. It was the first step, but it wasn't the ultimate one. So another person came along later, and his name was Schrödinger. And Schrödinger is one of the most fascinating of all these great chemists in the past. And if you're bored, it would be cool to look up some information on Schrödinger. He's a very interesting person. But through a long story, he ended up creating what's called quantum mechanics, which is his model of how electrons fit around atoms. And in Schrödinger's system, quantum mechanics, there were shells, but there's also what they call subshells. So if you look at this picture in the lower right-hand corner, this is like a campus, all right? And the students can be in dorm 1, dorm 2, dorm 3, and dorm 4. Dorm 1 has just one floor. Dorm 2, though, has 2 floors. And so they call the first floor the S floor, and the second floor would be P. But then dorm 3 has a first, second, and third floor, SPD, and the fourth dorm there, which is fancier and newer, I guess, has 4 floors, which they give letters to SPDF. Now, the maximum number of these floors, which are really subshells, all right, depends on the electrons and where they are, the energy electron number, and we'll see that here pretty soon. But this was a little bit better. So in the Bohr model, there was just dorm 1, 2, 3, and 4, but they were all basically like one story. But in the Schrödinger version, you could have multiple dorms, multiple shells, all right? But the shells had subshells in them. And SPDF is something we're going to talk about a lot, so remember that in the back of your mind. Quantum mechanical model of atomic structure gives some really cool information on electrons. Electrons literally are restricted to moving within just a certain part of the electron space. You'd think that the electrons could, for example, in that dorm idea, go back and forth between first one and third dorm, etc. But actually they don't. They always want to be in a specific place. They're not free to move about, and they don't exist like between the two dorms. Like you can't be in between. You have to be in a dorm, and you have to be in a certain subshell, at least in the ground state, which is kind of interesting. The position depends on the energy, all right? If the energy is high, then of course you'll have more variation, but if it's lower in the ground state, then it will be just in a certain place. Electrons, they say, the energies of electrons are quantized. They can only be in certain places. They can't be anywhere they want. So for example, you could have an electron which was in dorm 1, but it would be harder to get to dorm 2. And what's really interesting is that the electrons will never be halfway in between, all right? You can have at dorm 1, if you add a little energy, you can at least temporarily make it go up to dorm 2, but you're never going to be like halfway, or you're never going to be between the second and the third floor. So every time you hear about quantize, this means that there's set energies that they have to restrict themselves to. The electrons in an atom are grouped into shells, and the numbers of the dorms are like the shell. So this one is 1, 2, 3, 4, all right? And then subshells are like levels on the dorm. So dorm 1 only has one level, that's the S subshell. And dorm 2 has 2 levels, that has an S and a P subshell. And then dorm 3 would be SPD, dorm 4 SPDF, etc., etc. And yes, there is a dorm 5, and we'll talk about this later. Now, S is always lowest energy, so it gets filled in first. P would be next, followed by D and F, stuff like that. From quantum mechanics, from the actual quantum mechanics, then you actually get some really interesting information. And by the way, quantum mechanics is basically a type of a calculation. At Mount Hood Community College, if you take the calculus series up to 254, you have all of the skills to figure out how quantum mechanics works. It's not not simple math by any means, but I have done it before in my past. It takes, if you're into this stuff and you've got good programs, it becomes a lot easier. We're looking at the results of these calculations. All right, we're not looking at the calculations themselves, we're just looking at the results of them. In quantum mechanics, they find that the first shell has just an S subshell. And again, that's like dorm 1 there having only one level, all right? Well, our shell has just an S subshell, and you can see that there at the top. We're going to call the first shell 1, all right? The second shell, or the second N there, N of 2, it has both an S and a P subshell. So it has like 2 levels on that particular shell. So again, the letters are the subshells and the numbers are the shells. And you can see how the shells increase, the number of subshells increases. So by the third shell there, at the shell number 3, you have an SPD, and by the fourth shell, S, P, D, and F. And yes, it does go beyond 4, but these are the ones that are most important for what we're talking about right now. The number of subshells is equal to the shell number. So for example, in N equals 1, in the shell equals 1, there was 1 subshell. And in the second shell, there were 2 subshells, the S and the P. And as it says right there, shell number 3 had 3 subshells, S, P, and D. Within each subshell, electrons are further grouped into orbitals. So in the analogy there of the dorm rooms, all right, you can think that first of all, there's the dorms, which are like shells, and then there's levels to the dorms. Those are the subshells. The orbitals are kind of like rooms in the shells, in the subshells, all right? And that's kind of important too. And each orbital we're going to see can hold 2 electrons. So in a normal dorm room, the students are paired up, all right, 2 students per dorm room. That's kind of the equivalent here for the orbitals. So there's different number of orbitals within the various subshells. So again, if you want to use the real world analogy, we would say there are a different number of rooms between the different levels, subshells, of the dorm room's shells. So here's our thing once again. So the first shell has only 1 subshell, the S, and there's only 1 room. So that's a single room. So the first dorm room has just 1 level and 1 room, or the first shell has just an S subshell with 1 orbital. Now, the second dorm room is a little bit fancier. It has 2 levels. Or 2 subshells. It has an S and a P subshell. And the S still holds just 1 room, or 1 orbital, but the P holds 3 rooms, or 3 orbitals. So you can imagine the P is a little bit fancier. And then going on to the next one, you can see how it goes SPD. The S holds just 1 orbital. The P holds 3 orbitals. The D would hold 5 orbitals. So by the time you get to the N equals 3, or the third shell dorm room, there are 3 levels, and that top level holds 5 rooms. And the next one goes even farther. Now, let's take a break for just a second. There's a lot of patterns in quantum chemistry, and you're probably seeing them here. So the shell is increasing in whole numbers, 1, 2, 3, 4, 5, etc. The number of subshells is equal to the shell number. So there was S in 1, there's S and P in 2, there's S, P, and D in 3, S, P, D, F, and 4. And yes, if you went to the 5th one, you'd have S, P, D, F, and G, but we won't talk about that so much here. And then look at the number of orbitals. Every time there's an S, then you have 1 orbital. Every time there's a P, there's 3 orbitals. D would have 5. Notice the patterns here, 1, 3, 5. F, the next one, would have 7. And even though I said I wasn't going to mention again, the G would have 9. Patterns exist all over the place in quantum chemistry. Now, we're just going to look at the simpler ones here, but hopefully you're seeing some of the things that make this stuff work. Orbitals, the rooms in the subshells, and the subshells are in the shells. The orbitals actually have different shapes, and this will be important sometimes for when you have electrons coming together. You have to have the right shapes kind of interacting. The first one is the S, and if you remember back from the picture we saw of the dorm rooms, the S level was the first one, or the subshell. And that one is very simple. It only holds 2 electrons. S basically looks like a sphere. They're spherical, all right? And that's where the S comes from, spherical. And so in a spherical S subshell, that's where the electrons hang out. And again, in each one of those little pictures, you can have 2 electrons hanging out there. It's kind of like a dorm room. So if you're curious what the first dorm room looks like, if you will, that would be one of these S orbitals. That sphere holds 2 electrons, which is kind of cool. Now, the ones on the right are called p subshells. So again, A is basically like a S orbital. These ones over here are p orbitals. And there are 3 orbitals in the p subshell, and that's what they quote unquote look like. So again, the real world analogy here is that those are the rooms in that p subshell, that p level of the dorm, all right? And the reason why there's 3 is that you can probably see all of these somewhat figure 8 looking things, or dumbbell or infinity, whichever one of these you like. They all exist along a different axis. So let's call this first one, the black line that goes right down the middle, let's call that the x-axis. Well, in the middle one there, maybe this then would be the y-axis. So see, it's a different axis it's oriented along. And then the third one, this up and down one, that would be z. So these are the 3 rooms in this level of the dorm, or in chemistry world, these would be the 3 orbitals in the p subshell. Each one of those little pictures, the S and the 3 P's, each one of those holds 2 electrons. And that's really important. Just like a dorm room can hold 2 people in theory, each one of those would hold 2 electrons as well. You can draw out pictures for d orbitals and f orbitals as well. They're somewhat like this, a little bit more complicated, but that's kind of the idea behind them. If you think about the total number of electrons that's possible, shell number 1, the first dorm room, had a single subshell, a single value of a letter, which was S, and there was 1 orbital, and all S subshells have 1 orbital. There's always 2 electrons per orbital, so that means it can hold up to 2 electrons. Now, in the second shell, number 2 in that dorm room, there were 2 levels, an S and a P. All the S levels have a single orbital, which means they hold 2 electrons. But that dorm was fancier. It had a second level, all right? It had the P subshell. And P subshells have 3 orbitals. Again, that's where you have the x-axis, the y-axis, and the z-axis, those kind of figure 8 looking things. Each one of those holds 2 electrons. So 3 orbitals times 2 electrons, 6 electrons total. So that means in the second dorm room, dorm number 2, you can have up to 8 electrons, or 8 students, all right? So notice here a couple of things. First of all, S had 2 electrons in both 1 and 2. P had 6. And that's going to be a pattern we're going to see throughout these. Now, remembering the patterns we talked about earlier, S's in the third dorm room, in the first level, the S subshell, 1 orbital and 2 electrons. And in the third dorm room, there was also a P level with 3 rooms, 3 orbitals, and 2 electrons per orbital, so 3 times 2, 6 electrons. But the third dorm room had a D subshell as well, an even fancier area. And Ds hold 5 orbitals. Again, notice the pattern, 1 orbital to 3 orbital to 5 orbitals, and 5 times 2, it holds 10 electrons. So the third shell, third dorm room, holds 18 students, or 18 electrons. And you can keep going. So number 4 has SPDF. The number of orbitals in each of those subshells, 1, 3, 5, 7. Again, the pattern. Electrons go from 2 to 6 to 10 to 14, holding up to 32 electrons. And again, you could do this for shell number 5, etc., etc. This leads us to the place where we can start making what's called an electron configuration. And this is the exact arrangement of electrons in the atom shells and subshells. And there's some rules to do it, and they're not real hard, but it does give chemists then a better understanding how the electrons fit around the atom. Electrons always go to the lowest energy orbitals first and work their way up. So in the idea there with the dorm rooms, that would mean that students always go to the first dorm room and then they start filling up the second dorm room. And they like being closer to the ground, if you will, than they do the other ones. And we'll talk more about the orbital transitions later possible. Each of the orbital holds only 2 electrons. Now remember that when you see a p, that can mean a subshell. P subshells have 3 orbitals. So each of those px, py, pz holds 2, and the same thing for the other ones too. The electrons, there's only 2 of them because they have what's called opposite spin. And spin is actually how the electron is arranged around a magnet. And we're going to see you can have spin up or spin down, but you can't have like a spin up next to a spin up or a spin up or a spin down next to a spin down. If you have 2 electrons in an orbital, one is spin up and one is spin down, and that's kind of a cool thing too. If 2 or more orbitals have the same energy, then each gets 1 electron before any orbital gets 2. So going back to the p subshell, p's have the px, py, and pz. You would put 1 electron in each of those orbitals first before you started having 2 electrons per orbital. And we'll see how this works out here in a little bit. The electron filling order is an important part, and in the Bohr model of the electrons, he thought only about the shell. So if you look at those little lines on the right side there, shells go 1, 2, 3, 4, 5 in order like that. But in reality, it's a mixture of shell and subshell which determines the order. And so you can see there how 1s is always first. That would be like the first shell and the s subshell. Then you go 2s and 2p, no problem. But then look what happens. You go 3s, 3p, 4s sneaks in before 3d. Then you go 4p, 5s sneaks in, stuff like that. So this order of how the electrons get put in is really important. But on a practical level, focus on those letters. Every time you see an S, it's going to hold 2 electrons. So the 1s will hold 2 electrons, the 2s will hold 2 electrons, the 5s at the top will hold 2, and likewise, the p's will always hold 6. So 2p, 3p, 4p will be 6, d's will be 10, stuff like that. Pretty chill. Here's a little video we can watch to see what more about the electron configurations.
In the modern theory of the hydrogen atom, or any one electron ion, all subshells with the same principal quantum number n have the same energy. Theory tells us, however, that in atoms containing more than 1 electron, the repulsive interactions of the electrons with one another cause subshells of the same principal quantum number to differ in energy. The 1 electron in the hydrogen atom, in its lowest energy, or ground state, occupies the 1s orbital. In helium atomic number 2, there are 2 electrons. Where does the second electron go? The first rule is that electrons occupy the lowest available orbital. The second rule follows from the Pauli exclusion principle. Any orbital can hold at most 2 electrons of opposite spin. These rules tell us that in helium both electrons occupy the 1s atomic orbital. With increasing atomic number, the electrons occupy orbitals of increasing energy. With carbon, we encounter a new question. Because there are 3 degenerate 2p orbitals, that is, orbitals of equal energy, Hund's rule tells us that with 2 or more orbitals of the same energy, we should place electrons singly in each, with parallel spins until all are half full. With nitrogen, we arrive at a half-filled subshell. A half-filled subshell is associated with special stability. As we come to oxygen, having used up all the vacant 2p orbitals, we must pair electrons. With neon, we come to the end of the first row of the periodic table, and the stable octet of electrons in the outermost shell.
Okay, there was a lot of information in that video, and we're going to go over it here in a little bit. But I do want to get a couple of ideas across. What you can see is those were electron configurations for some of the atoms. And the first thing you must know is how many electrons do the atoms have. And that's what you go back to the periodic table for. So for example, hydrogen is number 1. That's the atomic number, which means really number of protons. But in a neutral atom, electrons and protons will be the same. So hydrogen would have 1 electron, helium would have 2 electrons, lithium would have 3, etc., etc. The next thing that's important is that electrons always go to the lowest orbital first and work their way up. So electrons will always start at the 1s, which is the lowest, and then after that's filled, go to 2s. So for hydrogen, the 1 electron went to the 1s and it stood there. All right. The second electron also went to the 1s. You want to fill up the lower ones first before you go to the higher ones. And you could see there was an up arrow and a down arrow. That represents spin up and spin down. And in a box, in an orbital, you can only have 2 electrons, 1 spin up and 1 spin down. When you got to lithium, then you put the third electron in the 2s orbital, because now there was no more room in the 1s, 2 electrons only per orbital, and you'd start filling it up. And then finally, when you get to carbon, you can see that you have 3 orbitals that are the same energy, and that's the 2p set. So you'd have 1 electron in the first 2p, and you'd put the second electron in one of the separate boxes. Don't pair it up. Pairing takes a little bit of energy for electrons, so you want to have them separate whenever possible. Now, that was probably as clear as mud, so let's go through some examples and see if we can make some more sense of all of this. When you're filling up electrons, you always want to follow this order. 1s is before 2s, 2s is before 2p, 2p before 3s, before 3p, 4s sneaks in before 3d, etc., etc. And some people have really good luck just memorizing this order and using it, and that's fine. And remember, s's hold up to 2 electrons, p's hold up to 6, d's hold up to 10, etc., etc. There's other ways to do it too, and I'll talk about those in a little bit. So you want to start always with the lowest energy level, which is sublevel, which is subshell, and that's 1s. And then once you have 2 electrons in 1s, you go to the 2s. Anytime you have an s, it holds 2 electrons, so 2s would also hold 2 electrons, just like 1s, but p's will hold up to 6. So when you fill up the 2p with 6 electrons, that's when you go on to 3s, etc., etc. And you basically stop when you run out of electrons. Each of the s's will hold 2 electrons, each p will hold 6, d will hold 10, f will hold 14. And yes, you can go past it, but really just going up to f is fine most of the time. All of the s subshells will hold 2 electrons. 1s, 2s, 3s, 4s, 5s, 6s. There's a bunch of them, but they're always going to hold just 2. And also, all of the p's will hold 6. So 2p, 3p, 4p, yes, there's a 5p and a 6p, etc. Those will all hold 6. Now, I like using what's called an Aufbau diagram, and that's what this thing is. Aufbau is a German name for order or something like that. And you can see, you can build one of these really fast just on a piece of paper. You start off with 1s at the top, and you just go 1s, 2s, 3s, 4s, 5s, etc. You go as far as you want. Then you go down and write one where you start with the 2p, and you go 2p, 3p, 4p, 5p, etc. Then you move down and 1 and go to the D's, 3D, 4D, 5D, 6D, move down and 1 to go F, etc., etc., etc. And those little arrows right there, which start with 1s, then you move around and go 2s, 2p. That's the filling order. So 1s is first, and then 2s is next, 2p, 3p, 3s, and then you can see 3p and 4s sneaks in before you go to 3d, etc., etc. So Aufbau diagrams are really cool, and I recommend that you practice drawing one so that you know how this all works out. So let's do some examples. Let's figure out the electron configuration for magnesium. And if you look on the periodic table, magnesium is number 12. Z is the atomic number, so that means 12 protons, but in neutral magnesium, you'd also have 12 electrons. Well, you want to start at the lowest those subshells, which is 1s. And remember, 1s always holds 2 electrons. So we've got 12 electrons total. The first 2 go in 1s, so we got more electrons to go. The next 2 would go in 2s, because again, s's always hold 2. Then we move to the 2p. p's always hold 6 electrons. And finally, the last 2 electrons would go in the 3s. Now notice that nomenclature. It was the subshell, 1s first, and a superscript in the right-hand corner representing the number of electrons. So 1s2, 2s2, 2p6, 3s2. That's how that goes. And again, you always want to start with 1s, move to 2s, move to 2p, etc., etc. And that's really all you do on these, all right? Start with the 1s, move your way up. If you get lost, add up all of the superscripts. So if you add up 2 plus 2 plus 6 plus 2, you should have 12, which is the number that you want for neutral magnesium. Nothing wrong with adding up the superscripts, mind you. I've done that myself before. But anyway, yeah, that's what you do. Boron is number 5 on the periodic table, so that means 5 protons, and neutral boron would have 5 electrons. Now for boron, we're going to start with the 1s again. We're going to fill up that 1s. We're going to fill up the 2s, because again, 2s only holds 2 electrons. But since we have 5 electrons, the 5th electron is going to go in the 2p. So we would write it as 1s2, 2s2, 2p1. And notice there how it's okay to have an incompletely filled subshell, all right? So having 2p1, 2p2, 2p3 is totally fine, all right? You would never want a 2p7, p's only hold 6, just like you'd never want to have, for example, a 2s3, because s's hold just 2, but it is okay to have them underdone. Now, on the right-hand side here is what they call orbital box notation. The 1s, all right, this represents the orbital. And you can see there's an up arrow and a down arrow. That's that spin we talked about earlier. So 1s2 would be 1 up electron and 1 down electron. And in 2s, right next to it, 1 up and 1 down, no problem. But then when you get to 2p, we have only 1 electron. So people usually write up first instead of down. You can write down first instead of up if you want to. But anyway, you would write just 2p1 with 1 arrow. And the arrow could be in any one of the boxes. It doesn't matter. This person has written it with the left side, which is fine. The 1s2, 2s2, 2p1 is sometimes called spectroscopic notation, and it's a very compact way of doing this. However, we're going to see that this on the right, which is called orbital box, also has some uses to it as well. So you'll see both ways in this section. Here's the boron once again, 1s2, 2s2, 2p1, spectroscopic on the left, and the orbital box notation version on the right. And again, they're both really useful. One thing that the orbital box notation does is it shows if you have something that's paramagnetic or diamagnetic. And boron has this individual electron in its own orbital by itself. And for reasons which we'll talk about more in the 200 level, that makes that electron a lot more reactive with things around it. And things that are by themselves, electrons by themselves, that are spin up without a spin down, or even spin down without a spin up, they're called paramagnetic. And paramagnetic electrons are very, very reactive, all right? They react in our bodies, they react in Mother Nature, outside, and stuff like that. They can do both good things and bad things, but it's good to know if you have one or not. So, in this example, boron is a paramagnetic atom. It has an odd electron by itself. Magnesium, we saw on the last page, would be an example of a diamagnetic atom. And it's diamagnetic because in magnesium, every up electron has a down electron. So magnesium had a 3s2 on the outside. That would be an up and a down, just like 2s2 right here. Magnesium would be diamagnetic, while boron is paramagnetic. Now remember, you've got to have 1 electron per orbital, all right? And that's going to be important to us coming up here soon. So we would say boron is paramagnetic because of that one electron that is up without a down or down without an up. So there's boron, again paramagnetic because of that 2p1 part right there. Magnesium, 1s2, 2s2, 2p6, 3s2. Notice that magnesium has just as many ups as it has downs, and every one of those little boxes is filled. So magnesium is diamagnetic, and diamagnetic electrons are not very reactive compared to paramagnetic things. It's an important distinction to make. Most of the things that we deal with in our life are actually diamagnetic, but when you do run into paramagnetic things, there's lots of possibilities, shall we say. Carbon, 1s2, 2s2, 2p6. Again, carbon is number 6 on the periodic table, so the first 2 electrons go in the 1s, next 2 go in the 2s, and then the last 2 go in 2p. Now, when you're doing orbital box here, 1s2 and 2s2 aren't too surprising, but 2p2 is worth commenting on because you could have carbon with an up electron in the same room as a down electron, like they both would be in the same little line, the same orbital. But you always want to write them in individual orbitals first. So you wouldn't have an up and a down in the 2p. You could, right? You could erase this one and you add the down right there. But you don't want to do that, all right? That's bad, bad, bad. In chemistry, each electron goes in their own room. And I like to think about that as if you've ever lived with a brother or sister. If you have to be in the same room, like share a room, you can, but it's much nicer to have your own room. All right, you can put your own posters up, or I don't know, have your own books available. It's just nicer to have your own room, okay? And electrons want to have their own room too, if possible, but if they can't, then they'll start to pair up. So carbon is paramagnetic because it has unpaired electrons. Nitrogen is 2p3. It has one more electron than carbon. So nitrogen is also paramagnetic. It has 3 unpaired electrons. Again, you don't pair up anything until you have to. Those electrons want to be in their own room if they can. Phosphorus, which is right below nitrogen, looks kind of like nitrogen. And we'll talk about this more in a little bit. Now, phosphorus is number 15. So 1s2, 2s2, 2p6, then 3s2, 3p3. But notice this part right here to the right of my red line. Both nitrogen and phosphorus have s2p3 outermost electrons. For nitrogen, it's 2s2, 2p3. For phosphorus, it's 3s2, 3p3. That similarity we'll talk about here in a little bit. But regardless, phosphorus is also a paramagnetic atom because of the unpaired electrons. This periodic table kind of thing right here talks about the regions or blocks on the periodic table. And the periodic table is actually based around these rules. So we saw earlier that, talked about earlier, how hydrogen and helium are the 1s, 1s1, 1s2. And notice here how hydrogen, which would be right there, and helium on the far right, those are both 1s. And then lithium and beryllium would be the next two right there at 2s. 2p would be boron, carbon, nitrogen, oxygen, etc., etc. So those are the blocks where you're filling in the electrons, and the outermost electrons are usually the ones that are more reactive. So that's why it's kind of nice to know. The left-hand columns are what they sometimes refer to as the S block. S's always hold 2 electrons. That's why there's 2 columns right there. And the right-hand side, ignoring helium, which should be on the right-hand side there, there's 6 electrons, and that's because of those p subshells. P's always hold 6. And if you count the number of boxes in the middle, there's 10. Those are the D subshells. And lanthanides and actinides should, anyway, have 14. There's some weirdness down there we'll talk about later, but they should have 14. So again, you're seeing the patterns, 2, 6, 10, 14. Those are the number of electrons per subshell, comes straight from quantum mechanics. So you can argue that the periodic table, in part at least, is set up because of quantum mechanics, which is kind of crazy. So here's just some more examples. Hydrogen has 1 electron, 1s1. Helium, 2 electrons possible in every s orbital, so 1s2. Lithium, 3 electrons, 1s2, 2s1. Beryllium, 4 electrons, 1s2, 2s2. So far we haven't filled in any of the p's because we're just filling in s's. Again, you've got to fill the lowest ones up first and then move on to the highest ones. So all 4 of those elements, hydrogen, helium, lithium, beryllium, they would be referred to as s block elements because you're filling in s electrons. The next ones, boron through neon, is when we start getting into the 2p's like we saw. So boron would have the 1s2s2 core, but it would have a 2p1, carbon would have 2p2, nitrogen 2p3, oxygen 2p4, fluorine 2p5, neon 2p6. But they're all p block elements. They're all on the right-hand side of the periodic table. So if anyone ever asks you, the p block is on the far right, s block is on the far left, and anything in those sections would do it. And again, the s block is 1a, groups 1a and 2a essentially. Those are the s electrons, while the p block would be groups 3a through groups 8a, 6 electrons because of the 6 and p's. Sodium is group 1a, all right, it's an S block element. There's a little picture of sodium, by the way. Atomic number 11, which means 11 electrons. So sodium's electron configuration would be 1s2, 2s2, 2p6, the neon we saw before, which was all of this stuff, with a 3s1. But we're going to see that these electron configurations become so long after a while. So instead of writing out 1s2, 2s2, 2p6, 3s1 all the time, chemists will sometimes use what's called noble gas notation. And to do that, you go backwards to the most recent noble gas and just have it in brackets, and then anything not in the noble gas gets put on the outside. So 1s2, 2s2, 2p6, which I underlined there, that's neon. That's the neon electron configuration. So this little thing right here, neon in square brackets, represents that 1s2, 2s2, 2p6. And then anything past that is placed in it. So you could also write sodium's electron configuration as neon in square brackets 3s1. And I highly recommend it. The electron configurations will get really long if you don't. It's not wrong to do it. It just saves you time. I am a lazy chemist. I like to do things as efficiently as possible. You do have to go backwards to the nearest noble gas. If there's a noble gas just to the right of your element, sorry, you still have to go backwards and stuff. That's the way these rules work. All the group 1a elements, all the alkali earth metals, will have some kind of noble gas core NS1 electron configuration. So we saw earlier that lithium was 1s2, 2s1. That would be a helium core 2s1. And here sodium has a neon core 3s1. Potassium, last noble gas right before it is argon, so it's an argon 4s1. Rubidium, krypton 5s1, etc., etc. Notice the potassium is in the 4th period. Periods go left to right. If you've got a periodic table in front of you, check it out. If you don't, grab one. Pause the video and grab one. They're really important. Potassium group is period 4, and that's got a 4 right there. Just like sodium is period 3, and there's a 3 right there. So cesium would be the 6th period, so the most recent noble gas, xenon, etc., etc. Again, this is a really nice way to do electron configurations. There's nothing wrong writing it all out, but if you want to save a little time, totally cool. Again, here's the electron configurations using the block. Remember, helium for this discussion should be on the left side, but otherwise it's pretty good. Remember, we saw that 4s gets filled in before 3d. So you can see why then 4s here is first and then 3d in the middle. Anyway, it's kind of cool. Lanthanides and actinides, again, they kind of sneak down here. There's kind of like a gap and they kind of sneak down. So the actinides here, blah, blah, blah. Valence shell electrons are the outermost electrons, and those are usually the ones that are the most reactive. And for a lot of the molecules we're going to talk about in the Chem 200 series, the valence electrons are the ones we're going to be after. And it's pretty easy to determine how many valence shell electrons an atom has. And again, those are the ones that are going to make molecules. Here's phosphorus again. 1s2, 2s2, 2p6, 3s2, 3p3. And out of all those 15 electrons, the question is like, which ones are more reactive? Well, for this discussion, you can think about where the phosphorus is right now. That's the nucleus, and it's very positive. So it pulls really tightly on the closest electrons. And this configuration is written for a reason. 1s is closest. So 1s is deep in phosphorus. It's right next to those positive charges. No way, well, very difficult to get those away. Now, phosphorus pulls pretty well on 2s because it's not too far away, and it pulls fairly well on 2p. But when it gets to 3s and 3p, those are getting quite a ways away from the nucleus. So the valence electrons are literally just the electrons which are furthest from the nucleus, and they're a little easier to be dislodged. You can do things with them because phosphorus is being shielded by the inner electrons. So phosphorus then, that 3s2, 3p3, that's the number of valence electrons. Phosphorus has 5 valence electrons. Now, remembering that phosphorus has a total of 15 electrons, if you look at the periodic table, that means phosphorus has 5 valence electrons, and it has 15 minus 5, 10 core electrons. Core electrons aren't as important right now, but they can be cool. Those core electrons are just the ones which are less likely to react. So valence electrons, again, are pretty important to chemists because those are the ones that are going to make molecules. And it's pretty easy to figure it out. The number of valence electrons is just equal to the group number for that atom. And again, we're using the quote-unquote American version of the periodic table where there's A groups on the far left and the far right, and B groups in the middle. But anyway, carbon, if you look at it, is group 4A. The 4 is the number of valence electrons. So carbon has 4 valence electrons. Now carbon has a total of 6 electrons, but the other 2 electrons are so deep in the atom that they're not likely to react. We would call the other 2 electrons core electrons. Notice that core plus valence equals total electrons, but really just focus on this part. Valence electrons equals group number. Now bromine is in group 7, so that means it has 7 valence electrons, and all the other electrons in bromine, I think it's like 28, those are all core, not very exciting. It's the valence electrons which are exciting for chemists. So let's test ourselves here. Let's find the electron configuration for arsenic and figure out how many valence electrons are in arsenic. So you do need, of course, a periodic table in front of you. Arsenic is right under phosphorus, all right? And if you look at that, arsenic ends at the 4p region. So nitrogen had a 2p3, phosphorus had a 3p3. That means that arsenic is going to have a 4p3. But the difference here is that arsenic has a lot more electrons. It's got 33 electrons. So let's start by putting them in the 1s, 1s2, then the next one's going the 2s, 2s2, then 2p6, that gets us up to neon. 3s2, 3p6 follows, that gets us up to argon. Then we get 4s2, 3d10. Remember, D's have 10, P's have 6, S's have 2, 3d10, and then the last 3 electrons, 4p3. Of all of those electrons, arsenic has 5 valence electrons. It's in group 5A. So the 5 tells you what it is. We're going to talk about this more in the 200 level, but 4s and 4p, the bigger number in front of it, those are the outermost electrons. So that's where the 5 valence electrons comes from, and the other ones would be considered core. Calcium, we can do the same kind of thing. Let's figure out the calcium electron configuration and how many valence electrons. No problem. Calcium has a total of 20 electrons. So we start again, 1s, 1s2, all s's have 2, 2s2, 2p6, that gets us to neon. 3s2 3p6 gets us to argon, and then 4s2 outside of that. You could also write calcium as argon, Ar in square brackets 4s2. That would be the noble gas notation, and that's fine. Calcium is in group 2a. The 2 tells us it has 2 valence electrons. Finally, in this chapter, we're going to look a little bit at the sizes of atoms. And there's a trend on the periodic table that follows the size of atoms fairly well. All right, it's not perfect. They call this kind of analysis a periodic property. It's a property that can be kind of gleaned out of the periodic table by the nature of its position. So this is a reference to the sizes of neutral atoms. And the picture on the right there has the relative sizes of the atoms. And if you look at the green ones and the yellow ones, basically they're all getting bigger as you go left and down on the periodic table. And that's a pretty good trend. When it comes to all the elements on a periodic table, the sizes of the atoms get bigger as you go left and down. So this is the punchline. If someone asks you what the biggest atom is between two of them, you want to look for the bigger atom will be more left and down on the periodic table. So let's look at, for example, aluminum and silicon. Aluminum is bigger than silicon, most likely, because it's more left on the periodic table. And if you compared, I don't know, argon to krypton, we would say that krypton is bigger because krypton is more down on the periodic table. All right? Now, I would never ask you questions where, for example, one atom is more left and one is more down. So nitrogen and sulfur would be an unfair question, in my opinion, for me to ask, because one is more left and one is more down. I would argue that down is more important than left, and you can kind of see that from the pictures of the atoms, and look smaller than sulfur. However, that's not a for sure thing, and you should be very careful. Now, do realize that these are trends, and if you look at the actual numbers, they don't always pan out. So if I remember right, like iodine is smaller than xenon, and iodine's more left. So this is kind of an overall trend. It's not perfect, but if you don't have Google on your phone or an internet connection, and someone asks you this question, you can still sound like you know what you're doing by using the idea that sizes get bigger as you go left and down on the periodic table. Atomic sizes get bigger as you go down of representative elements. This works usually pretty good. And again, the sizes getting bigger means the distance from like the outside of the atom to the nucleus. And generally speaking, they do get bigger as you go down. As you go across the period, it's a little bit more strange, but it has to do with the shielding of electrons, which is kind of strange. And they'll talk about the different charges and stuff like that. As you go left, they get bigger. As you go down, they get bigger. We'll talk more about why this is the case in the 200 level. So here's some questions you might see. Which neutral atom is bigger, calcium or bromine? And that's a really good question. Again, to answer this, you look for the element which is more left and down on the periodic table. And calcium is certainly more left. It's a metal. Bromine is a nonmetal on the right. So we would predict that calcium is the bigger one. If we were looking for the smaller one, of course, we'd look for bromine. It says which neutral atom is bigger, calcium or radium. So remember the rule, bigger ones are left and down. In this case, radium, Ra, is further down the periodic table than calcium. So we would say that radium is bigger than calcium. Calcium is smaller than radium. All right, you get the idea. And again, these are just trends. And there are other periodic trends that we'll talk about in the 200 level, but this gives you an idea of what it's all about. Okay, that's the end of chapter 3. Sections 3.3 through 3.5, an introduction to electrons and how they work around the atom. We'll look at this more in the problem set. If you have questions on this material or anything else, please reach out to me. I'm more than happy to help. Have a wonderful day.